So here is the PV diagram of this problem. Okay. So the working substance is gas, so there is no need to show the dome. So this is the initial pressure and initial volume. This is P1, which is 200 kilopascal. Initial volume is V1, which is 0.05 meter cubes. Final pressure, which we have now calculated, that is 320 kilopascals. So for example, this is 320 kilopascals. P2, and final volume, which is 2 times of V1, that is V2, which is equal to 2 times of V1. Now, because this piston is attached to a linear spring, that's why the path between this initial state 1 and final state 2 will be a linear or straight line. So we can join these two lines, these 2 points directly with a straight line, because that is attached to a linear spring, and that's why this change from state 1 to state 2 will be a linear change. So now we need to calculate the work done, which is the area under this curve. This is the total area under this line 1 to 2, and this area represents P dV product. So which we can calculate directly from here because it is a trapezoid, or we can divide it into 2 parts. So now this is area 1 and this is area 2, right? So first we can calculate this area, which is simply the area of this rectangle, which is given by V2 minus V1 into P1, plus this area, which is a triangle. So 1 by 2 BH is the area of this second. So then sum these 2 areas, and that will be the total area under this curve, which represents work done during this process 1 to 2. That is work done from 1 to 2. So that is shown here on this diagram, PV. So now the area of part 1 is 0.05, this delta V into this pressure, which is 200 kilopascal, and that area represents 10 kilojoules. So this 10 kilojoules is actually this area 1. Second area, which is a triangle. So triangle area is given by 1 by 2 into B. This is breadth into this height, and this height is 120. Total is 320 from here. So 320 minus 200. This is this height, which is 120. 120 multiplied by this side, which is volume, multiplied by 1 by 2, so that is area 2, and that is 3 kilojoules, means this area. So the total work done is given by 10 plus 3, 13 kilojoules. And the part C is to find out the fraction of this total work, done against this spring to compress it. This is the total work done, but this work is done against this pressure, 200 kilopascal, and this work is done against the spring pressure. This part, this triangular part, represents the work done only against the spring force or the pressure developed by the spring. So the fraction of this total work, which is 13 kilojoules, how much is of spring? So that is only 3 kilojoules. So that was part C. Now let's solve another problem. A rigid tank. So we already know what is meant by rigid. Rigid means the volume is fixed So here is a rigid tank shown, is divided into two equal parts. So here is the rigid tank, which is divided into two equal parts by a partition. So here is the partition. Initially, one side of the tank, the one side of this tank contains 5 kilograms of water here in this one side at 200 kilopascals. So the pressure over this water is 200 kilopascal and temperature of 25. So it means the initial temperature of this water is 25 degrees Celsius. And the other side is evacuated, means this second side, the other side is evacuated. Now what happens is that the partition is then removed. Now this partition is removed. This partition is removed, and now the water is free to expand in the entire tank, and the water expands into the entire tank. The water is allowed to exchange heat with its surroundings. So here is an important thing, that when we take this partition out, now the water is free to expand. So when this water will expand, its volume will increase, pressure will drop, because now it is expanding. When a substance expands from smaller volume to a higher volume, its pressure drops, volume increases, and what will be the effect on temperature? Temperature will also tend to drop, because now volume is expanding. Maybe some of this water evaporates, because now volume increases, pressure drops, and pressure drop, maybe the pressure drop is so significant that some of this water vapor, if it is in liquid form, then some of this liquid water may evaporate. And when this water will evaporate, of course it will absorb heat from somewhere, right? For example, this the outside wall of this cylinder is not insulated, so it means heat will be absorbed by this water from the surroundings, right? And that's why some of the water may evaporate during this process. So when it takes heat from the surroundings, so initially what happened, when the partition was removed, water was allowed to expand, volume was increased, pressure was dropped, and there was a tendency for the temperature to drop also. But as the temperature drops, water absorbs heat from the surroundings, and the temperature will be attained. The initial temperature is again attained. So that is what is written here. The partition is then removed here, and the water, this water expands into the entire tank. The water is allowed to exchange heat with its surroundings. So it means it can exchange heat with the surroundings, either into the system or out of the system, because this outer wall of this cylinder is not insulated. That's why it is allowed to exchange heat with its surroundings until the temperature in the tank returns to its initial value of 25 degrees Celsius. So it exchanges heat so that the temperature which was dropped when this partition was removed, that initial temperature is regained or re-achieved. So this is the process which occurred in this tank, that initially there was a partition. One side was filled with water at this pressure and temperature, and this is the total mass of the water. Now partition is removed, water is free to expand in the entire tank. When it is expanding, its volume is increased, pressure is dropped, and then of course temperature will also drop. But as the temperature drops, it may absorb heat from the surroundings, because temperature is dropped, there is a temperature difference available, and some heat may flow into the system, so that the initial temperature 25 degrees Celsius is again re-achieved. So T1 was 25, and after this process of removal of partition and expansion of water and the heat transfer, The final state, at final state, temperature is again 25 degrees Celsius. So what is the unknown? So now we need to determine the volume of the tank. Volume of this whole tank is to be determined. And then the final pressure, P2, and the heat transfer for this process, Q. So these are the three unknowns. So you can see here the part A is to calculate the volume of the entire tank, V tank. So how we can calculate the volume of the entire tank. So now we have to see what is the data which is given, on the basis of which we can find out the volume of this whole tank. So from the given data, we can see that we know the initial conditions P1 and T1 and the total mass of that substance, which is 5 kilograms. So if we can somehow find out this volume of water, right, which is equal to the half volume of this tank, right, so then we can find out this half volume. So the total volume will be 2 into this half volume, right? So we need to, because air pressure and temperatures are given for this fluid, which is water. So with the help of this given data, we will try to find out V1. So we can find out V1 corresponding to P1 and T1. So this will be the half volume at state 1. And the total tank volume will be simply 2 into V1. So that's how we can find out the volume of this tank. Now, how to determine this V1? That is the question. So now, first of all, we need to see how we can calculate V1 at this pressure and temperature. If this fluid is an ideal gas, then we can use PV is equal to MRT. But this fluid is not an ideal gas, that is water. But still we do not know at this state P1 and T1 whether it is superheated water, or it's a liquid water, or it's saturated water. That is not clear from this given data of T1 and P1. So first of all, we need to consult the steam table, and with the help of steam table we can find out what is the phase of that water at state 1. Phase means whether it is liquid, compressed liquid, superheated vapor, or saturated liquid or saturated vapor, or mixture, or in the mixture region. So first of all, we need to determine its phase, and once we know it is in liquid or superheated or saturated condition, then for that particular table we can find out its V1 for that pressure and temperature. Here we cannot use PV is equal to MRT because this is not vapor, or this is not an ideal gas, this is water. And also maybe this water is not in superheated region. So if it is in superheated region, even then we have to see whether we can use PV is equal to MRT or not. For water, in most cases we should not use PV is equal to MRT, because the water which we normally use at these temperatures and pressure, that will not be far away from its dome. It is near to the dome condition. Look at these values. These values are definitely near the dome, because for water the critical temperature and pressure are much higher than these values. So these values are much lower than the critical temperature and pressure. So it means we are definitely in the non-ideal gas region. So how to find out V1? To calculate V1, first of all, we need to see what is the condition of the water at this pressure and temperature. So for that, we should go to steam table at this pressure and at this temperature, 200 kilopascal and 25 degrees Celsius. So let's revise again what we have learned in chapter 3. We already learned in chapter 3. For example, using PV or PV diagram, we can tell, we can guess, or we can estimate the condition. or the region in which our substance may exist. So what is given pressure? Pressure, for example, this pressure line is 200 kilopascal line. So and this pressure, this is the saturation condition or mixture region, and corresponding to 200 kilopascal there is one fixed T set which is inside the dome, right? So for 200 kilopascal there is one fixed T set which we can see from the table. If this T set is lower than this T1, it means if this T set is lower than this T1, for example this is T1, then our substance is in mixture, in the superheated region. If this T1 is greater than T set we will see from saturated table for that pressure, and if our given T1 is higher than this T set, it means our substance at this T1 and P1 is in superheated region. But if this T1 is lower than T set for this pressure, for example if this is our T1, then this T1 line is intersecting this pressure line in the liquid region. So then this will be our the condition of our substance, working substance, which is water in this case. So let's go to the steam table and let's see what is T set at this pressure, 200 kilopascal. So here is the saturated water pressure table. For a given pressure of 200 kilopascal, T set is 120, and in our case this T1 is 25, so it means this T set for 200 kilopascal is 120. So this line is 120 degrees Celsius line, which is saturation temperature corresponding to this pressure, and our given pressure temperature is 25 degrees Celsius. So this temperature line is actually intersecting this pressure line in the liquid region. So it means point 1 is in liquid region. This state 1 is in liquid region. That is now confirmed. So that's how we we estimate the region in which the fluid is currently existing, the state or the phase in which the fluid is currently present at this pressure and temperature. That is definitely in the compressed liquid or subcooled liquid region, so which we have confirmed with the help of saturated table. So now the point 1 is in liquid region. So now we need to find out the volume V1 corresponding to this P1 and T1. So one thing is now clear, that at this point this state 1 is in liquid region. So for liquid region, how to find out V1? We want to calculate V1. So we can calculate V1 at this pressure and temperature. And for liquid region, what is our assumption, which we have learned in chapter 3, that V1 can be considered as Vf at that temperature. What is the temperature? 25 degrees Celsius. We can neglect the effect of pressure, and this value can be assumed to be here at the saturated liquid point corresponding to this pressure, this temperature of 25 degrees Celsius. So we can read V1 from the same table, for a given temperature of 25 degrees Celsius, and corresponding to this temperature, this is Vf, 0.001003 meter cubes per kilogram, small v1, which is equal to Vf at temperature of 25. The effect of pressure is neglected. Our pressure is higher than this one, but in the liquid region, the effect of pressure can be neglected. So let's go back. Right, so that is shown here. So V1, first we have identified where our substance exists in liquid region, and then for liquid region we know V1 can be calculated with the help of Vf, with the help of saturated volume, saturated liquid volume at that temperature, and that is 0.001003 meter cubes per kilogram. So now what we have found out from that table is specific volume. So the total volume will be this specific volume multiplied by mass m. Right? So total V1, capital V1 is equal to m into small v1. So 5 kilograms multiplied by 0.001003. So that comes out to be 0.001 meter cubes. So that is the volume of this portion, the half of the tank, or the volume of this water which is present in liquid form in this half, one half of this tank. So V of tank, what will be the volume of the total tank? 2 times of this one. So that is 0.005, sorry. So that value is 0.005 meter cube. So 2 into 0.005 is the total volume of the tank, which was part A. So you can see how we have calculated volume of the tank with the help by first calculating the volume of this water, which is present in half of the tank, and that was all liquid, compressed liquid water. Right. So now that is shown here, and that is calculated. That is part A, to calculate the volume of the whole tank. Now part B is to find out the final pressure. The final pressure, when this partition was removed, water was allowed to expand. So when water expanded, the total volume of this tank is fixed, right? So the volume of this water expanded and pressure would have dropped because volume is expanding. So that's why pressure would have dropped. So that pressure P2 at state 2, for which what is given? Only temperature 25 degrees Celsius. So now we need to calculate P2. So for state 2, what is given? Only temperature. Pressure is to be calculated. What about volume? Now initially the water was contained in this half of the tank, but now when this partition was removed, the water is allowed to expand in the whole tank, right? So it means the volume of this water, because some of the liquid may have evaporated. So now we have liquid vapor mixture in the entire tank. So the total volume of this tank is actually V2, the total V2, which we have calculated, V tank, divided by the mass, because now volume of the water is increased when the partition was removed. So it means for state 2 we also know V2, small v2, specific volume at point 2, which is equal to the total tank volume, V capital V2 divided by mass. This mass has been expanded in this entire volume. That's why the specific volume is increased. So V2 is 0.001 meter cubes divided by 5 kilograms. So that is new V2, small v2, 0.002 meter cubes per kilogram. Now at state 2, erase it. So at state 2, what we know now we know two things. One is temperature, second is now V2 is also small v2, specific volume. So now with the help of this T2 and V2, we will now try to calculate P2. Now we need to determine P2 with the help of this T2 and V2. So how we can find out, because now some of this water is expanded in the whole entire tank. So now let's see once again what is the state, or what is the phase of that water when it is expanded. Its pressure is dropped, temperature is dropped, and heat is transferred, so temperature is again regained. But what is the state, or what is the phase of that substance, if whether it is still in liquid region or it is when it has expanded in the entire tank, maybe all of the water is evaporated, then it would be in the superheated region, or it is in the mixture region. So now with the help of this V2, because now what is known for point 2 is specific volume, and for point 2 what is known, temperature. So at this temperature we can find out from the saturated table what is Vf and Vg. What is Vf and Vg? So then we will compare this Vf and Vg with this volume. If this volume is greater than Vg, it means this water is in superheated region. If this volume is lower than Vf, it means this water is in liquid region. If this volume is between these two values, it means our water is in two-phase region or within the dome. So let's see what is Vf and Vg at this temperature of 25. So let's consult the saturated table. So here is the saturated table for a given temperature. What is temperature? 25 degrees Celsius, and corresponding to this 25, what is Vf and what is Vg? That is 0.001003 and Vg is 43.34. Saturated liquid volume and saturated vapor volume, units meter cubes per kilogram. So our volume is 0.00. Let's go back. 0.002. So 0.002 is greater than this value and lower than this value. So 0.001002. So it is a little higher than this Vf and smaller, definitely smaller than Vg. So our water is in mixture region because its volume is a little higher or larger than this value, 0.001003, but our value is 0.001002. So although it's a very small amount of water is evaporated compared to this Vf, so but some water has evaporated, which we have confirmed now with the help of this saturated property table. So it means the state of our substance is mixture region. For state 2 at this T2 and V2 of 0.002, the substance is in mixture region, because we have seen what is Vf at 25 degrees Celsius and what is Vg, and this shows that our volume V2 is between these two values. So that's why it is in mixture region. So once it is in mixture region, so it means what will be the pressure. So we can read the pressure because it is at saturated condition. Mixture region simply means it's in mixture region. So for mixture region, that is the saturation pressure. Corresponding to this temperature, this is the saturation pressure. Let me show it again on diagram. We can show it on both PV or PV diagram. So let's show it on PV. On PV diagram, this was 200 kilopascal 9, and this was initial condition in the mixture region, right? Final condition, what was the final condition? Same temperature was same, so the final condition was somewhere in the on this temperature line, and now we have seen that this is in the mixture region. Final state 2 is in mixture region. So from 1 to 2, what has changed? Temperature is same, but at point 2 there is some low pressure is passing through this line, this one. So this was P1, 200 kilopascal, and this is P2. So we can find out pressure at this point 2, which is in mixture region, at this temperature, same temperature. T1 is equal to T2 is equal to 25 degrees Celsius. So we have seen it from the table. So we can see this pressure again from table, and that is P2, which is equal to P set at 25 degrees Celsius, and that is 3.1690 kilopascal. So from 1 to 2 on PV diagram, the pressure is reduced. So the same process can be shown on PV diagram also. Let's show it on PV diagram. This is pressure versus volume diagram. On pressure versus volume diagram, this line, for example, represents temperature of 25 degrees Celsius. And this was the point 1 was in liquid region. For example, this is point 1 in liquid region, temperature of 25 and pressure of 200 kilopascal. This pressure is 200 kilopascal. Now second point, the same temperature, because at point 2 we know the temperature is again 25, but pressure is reduced in this pressure. So from 1 to 2, your substance has followed some path which is not known, so that's why we can show it with the help of dotted line. So this is 1, this is 2 in the mixture region. So from 1 to 2 we can show it with dotted line because we do not know the exact path which it has taken from 1 to 2. So that is the process line on PV diagram. On TV diagram it is a horizontal line, and on PV diagram it is maybe a vertical or it may be a tilted line, right? So this is P2. And this P2 we have seen at this temperature. This point 2 is in saturation region, so that is 3.1690 kilopascal. So that is also shown here at the PV diagram. So from 1 to 2, that is constant temperature line, right? And from 1 to 2, it has followed some path which we have joined from 1 to 2. And area under this curve represents the work done during this process, because water has expanded, so it does some work against this pressure, external pressure. Okay, so this was point 2, point B or part B, to find out the final pressure. Part C is to find out the heat transfer during this process, because during this process some heat is transferred from 1 to 2. During this process some heat is also transferred, because when partition was removed, volume was increased, pressure was dropped, temperature was dropped too, and that's why heat was transferred to this fluid, and that's why its temperature was weakened to 25 degrees Celsius. So during this process, how much heat is transferred? So we can find out this with the help of energy equation, because this is a closed system. If this is our system, here is the system boundary. The walls of that cylinder is the system. So for this closed system, we can write its equation, or simply you can say E in minus E out. I'm using the general energy balance equation. E out is equal to delta E of system. That is first law of thermodynamics, and now we shall apply this law for this process between 1 and 2. So the energy going into the system is Q. There is no work done in going into the system, crossing the system boundary, so W is 0, but there is heat transfer Qi. So this is Q, which is going into the system, minus, is there any energy leaving the system? No energy is leaving, only entering, so that is 0, minus, that is 0. And during this process, what is the change within the system? Within the system, this delta E of system, it further consists of 3 parts: delta U, change in delta U, change in kinetic and potential energies. So neglecting kinetic and potential energy changes, this delta E is actually only delta U. So this one is actually delta U, capital U. So Q is equal to delta U. That is the equation of this process. Right. So using the same general energy balance, we have now derived the equation for this process, which is occurring in a closed system. So now del Qn is equal to delta U is equal to capital delta U, which we can write it as m into small u2 minus u1, right? So this delta U is actually equal to mass into small delta U. Small delta U is u2 minus u1. Final state minus initial state, that is the change in internal energy due to this heat transfer which is going into the system. Alright, so now we can value. So here is, I have explained how we have derived this equation. So now what is u1? Point 1 is in liquid region, so u1 will be equal to uf at 25 degrees Celsius, which we can see from the table also. Here is at 25 degrees Celsius, that is uf 104.83, and what is u2? That is in the mixture region. Point 2 is in mixture regions. For mixture region, we need to find out first x2, the quality, and quality we can calculate using this equation, the mixture region equation. V2 is equal to Vf plus x2 Vfg, which we have derived in chapter 3. So we first need to find out x2, because at point 2 we know volume V2, and at point 2 is at temperature of 25 degrees Celsius. So just put the values of V2, Vf and Vfg at the same 25 degrees Celsius. At 25 degrees Celsius, here are Vf and Vg. So put it here, all these values. So x2 is 2.3 into 10 to the power minus 5, because this point 2 was very near to liquid state, so that's why the value of quality is very low. So u2, now we can calculate u2, which is in mixture region equation, u2f plus x2 u2fg at 25 degrees Celsius. So put values from here, uf and ug or ufg, which is ug minus uf. So put these values to find out u2 and put it here. So you will see that this value is u2 is 104.88, the u1 was 104.83. So the change in u is very, very small after second decimal, because a very small amount of water is evaporated. That's why the change in delta U is very small too. So the heat transfer during this process is given by m into delta U, and that is only 0.25 kilojoules during this process. And our initial assumption was that Q is the heat is transferred to the system. So this assumption was right. If our initial assumption of heat transfer into the system would have been wrong, then the final answer would have been with negative result, with negative sign. So there is no negative sign. It means the initial assumption of heat transfer into the system was correct.